This is the first lecture on Chapter 17. There will be a second one, but this is for I period to get started. So what is Part 5 about? Well, it's from a sample or the data to the world. What does that mean? All right, we have a population right here. And information that we have about a population are called population parameters. What happened to my picture here? Here we go. And this. Okay. So population parameters are designated by the lowercase italic p. So we have a population, and from the population we take a representative sample. It's random and independent, not too big and not too small. And from that representative sample we have, here, let me erase this so it really looks like a P, lower case italic P. We take a sample statistic, which is designated by lowercase italic p with a little caret on top. It's called p hat. All right, now population parameters are always not specifically known. Their estimations, they're always changing. Populations, the truth about populations is always changing. If we want to know the proportion of people that support a particular candidate or, say, believe in evolution, as discussed in the chapter, obviously that number is always going to be changing. So, but the p-hat, the sample statistic that we get from the sample, is fixed, and that doesn't change. Now, if we take another sample, the p-hat will be different, but that a p-hat taken from a sample, a statistic taken from a sample, is fixed and doesn't change. Okay, now from that p-hat we get a probability, and we'll call that's going to be a p-value. We'll talk about that later. The p-value is the probability of the sample statistic occurring randomly if the population parameter is correct. Now, from the p-value we acquire the significance. The more unusual the p-hat looks, the more likely it is that our prior impression of the population parameter is false. So from the p-value we get significance, yes or no. And if the p-hat is significant, then it will alter our estimation of the population parameter. So in other words, we have the sample, we evaluate the probability of that sample occurring randomly, assuming that the population parameter is true, and from that probability we get a significance. If the p-hat is in fact significance, that is, it looks unlikely to have occurred randomly if p is true, then we will change our estimation of p. So that's what this section and really the whole rest of the course is all about. Now we start out where a couple of polls, Gallup poll and another one, I forget which, they poll up 1,007 U.S. adults, and they find the proportion that believe in evolution. So Gallup says, and there's another poll taken by the Baylor Religion Survey, talked about right here, from about 1,500 people, more or less the same size. And they find 41.9% agree with the basic idea of evolution. So two different samples and two different p-hats, the p-hat in one being 0.419 and the other being 0.43. And this is exactly what we should expect. The bigger the sample, then the more likely it is that each sample will have a different p-hat. Okay, now they ran simulations. Now we'll talk about why they do that in a minute, but the simulation was based on the idea that 43% is correct, and so they simply said, well, out of numbers 1 to 100, 1 to 43 is believe in evolution, and all the other numbers 44 to 100, we'll assume that you do not. Okay, so they ran this simulation 2,000 times. So what did they do? They created, simulation-wise, 2,000 p-hats. So in other words, they created 2,000 samples of 1,007 in size. And so each 1,007 persons, simulated persons, because what was the component? The component was one person's opinion. That's the component. And so they generated a 1,007 random numbers. And for every random number, and the numbers were between 1 and 100. And each random number that was between 1 and 42 was a person that believed in evolution. And each random number that was between 44 and 100 was a person that did not. And they did this 2,000 times. So they got 2,000 p-hats, and that's what this histogram is showing you, okay? It's showing you this is not the proportion of one of the samples of the people who believe in evolution or whatever. Rather, this is a distribution of all the different p-hats. Now notice, because the simulation was based on the fact that 43% of the people believe in evolution, it makes sense that the center of the distribution would be at 0.43. However, the thing to note is that this distribution of these sample statistics, called a sampling distribution, as you can see right here, okay, is approximately normal. Okay, so the sample size is 1,007, and then 2,000 statistics were taken from 2,000 sample sizes of 1,007. So here are 2,000 p-hats. And you can see there's a p-hat way over here with a pretty large percentage of people that believe in evolution. And here's a p-hat over here with a pretty small percentage of people that believe in evolution. Remember, these are all just the results of simulated trials using random numbers. The thing to understand, though, is that if you took actual polls of 1,007 people, so n equals 1,007, and you took 2,000 polls of that size that were random, independent, not too big, not too small, so they represent the population. Those p-hats, those 2,000 p-hats taken from actual polls would look just like this. In other words, the distribution would be normal. The distribution of those samples, statistics, called a sampling distribution, would be approximately normal. What would be different about the distribution of the actual samples is that they would be centered at whatever p really is. So if p were not 43%, but something else, that's what the center would be. Okay, now we have easier ways to compute the probability of a sample statistic than using a bunch of simulations, and that's what we're going to learn how to do. Okay, so let's look at this for example. Using the sampling distribution model for a proportion. Okay, according to the Centers for Disease Control and Prevention, 18% of U.S. adults still smoke. Okay, now this right here, that 18% is a population parameter. Okay, it's not a statistic. Maybe it was a statistic once in a sample, but it is an estimation. So we are going to say P equals 0.18. Oops. 0.18. And this is proportion. And whenever you say what a population parameter is, then you got to say what it is. Proportion of U.S. adults that smoke. Assume adults is going to be, well, they don't say what adults is. It could be 18 over or 21 over. I don't know. Okay. Now the question is, how much would we expect the proportion of smokers in a sample size of 1,000 to vary? Okay. Now in this case, they're doing simulations. They'll take random integers 1 to 100. 1 to 18 is a smoker, and the rest are non-smokers. And repeat the process. And they're going to get samples of 1,000 over and over. Now let's see how many times they're going to do this. And they did it 10,000 times. So N equals 1,000. So that's the sample size. And the repetitions, they got 10,000 p-hats. So each sample of size 1,000 yielded a single p-hat. That is a proportion, a simulated proportion of people that still smoke. Okay? And they did that 10,000 times. So this histogram here shows the 10,000 p-hats, the 10,000 sample statistics. Now we see how much they vary. It's symmetric and roughly normal. So the rules should work. The 68, 95, 99.7 rules should work. Okay? And you can more or less estimate the standard deviation simply by measuring the extremes and then dividing by 6. And they come up with a standard deviation of about 0.0122. Okay. Now, this sentence here is very important. Up till now, you thought of the sample proportion as a fixed value that comes from one particular sample. But now we're trying to understand how proportions from different random samples might behave. All right. Just keep that thought in your head. Each random sample has its own proportion, and each of those proportions may be different. So we really have to think of proportions as random quantities that vary from sample to sample. All right, so now we're going to get into some specific calculations here about how we figure the sampling distribution. Okay, so if there's a sampling distribution, it has a mean and a standard deviation. So the mu for p hat, we're going to call p. And the standard deviation, sigma, for p hat, which is the standard deviation for p hat. I'm writing this down, and the reason is, even though it's right there in front of me in the book, is so I'll remember it. So you write it down too on something if you think you're going to end up remembering this. Now this is a formula that will be given to you on the test. This is one of the ones they give you. But you're much better off if you know right away what these things mean. Okay, if you remember them. All right, and so you can see here's a distribution. Here's an approximately normal distribution for a sampling distribution, for any sampling distribution. Okay. Now, if we say for the people that believe in evolution that 43 is p, if we stick with p, then we can say that the standard deviation for the sampling distribution, for the distribution of sample proportions, however many there may be, is going to be square root of pq over n being the sample size. So it'll be square root of 0.43 times 0.57, q being 1 minus p, divided by 1007. So let's go over that again. Q equals 1 minus p. All right. Onward. Okay. All right. And then here's, here is the model based on the standard deviation that we just calculated, and saying that the center of the distribution is 0.43. Okay, and then here's the 68, 95, 99.7 distribution of stuff. Okay. Now, we have a normal model, so we can use 68, 95, 99.7 and look up and use normal CDF to get exact probabilities. Now, notice that these samples all varied from one another. Then the variation of p-hats from sample to sample, the fact that the p-hat is not always the same, in fact, is rarely the same. If the sample is big enough, it'll probably never be the same exactly. Sample variation is called sampling error. But it's best to just think of it as sample variability because there's really no error. Okay. Can we always use a normal model? Okay, this is a very interesting discussion here. This mathematician, de Moivre, proved that we can use the normal model with means. Now, what about proportions? Well, you can think of a proportion as a very weird sort of distribution made out of just zeros and ones. Anyway, that discussion is going to take place a little bit on the next page. Let me finish this off here. So let's just move on. What the point they're making here is that we're going to have trouble with proportions if p is close to 0 or 1. Then there's going to be trouble. You're probably not going to run into that too much here. Okay, let's go to the next page. All right. Now, assumptions and conditions. This is very, very important, and you must always prove that you can use the normal model and consequently can use the approximately normal sampling distribution to describe the distribution of your sample statistic by showing that your sample is independent, random, is not too big, the 10% condition, and not too small. NP and NQ are both greater than or equal to 10. Okay, now you just can't skip over this. You must prove specifically that each condition is met. All right. So let's use this thing. Let's go to the next page. So we got our sampling distribution model. All right. So let's use it for proportions. So let's go back to this. Okay. The CDC is a good source of population parameters. And here's another one. Okay. So the CDC says for the population of U.S. 22-year-old females, okay, for that population, 22% have BMI 25 or more. So for this particular factor, we're going to say P equals 0.22. Okay? And what's the population parameter for? U.S. women who have a BMI of 25 or more, that are 22 years old. 22-year-old U.S. women with a BMI of 25 or more. Notice it's fairly well qualified. Okay? Okay, is it unusually small? Now, note, you must state. They say it's a random sample. Okay, what do they do here? They say CDC, Physical Education Department, requires students to come in. This year, department's trying to. It has 200 randomly selected students to report their heights and weights. Okay. So they're randomly selected. Now you have to say, you just can't assume that whoever's reading the problem already knew that it's random. You have to say that you read it and you know that it's random. The department drew a random sample, so the respondents should be independent and randomly selected from the population. You have to say that. Everything that's in here is required for an answer that's going to be correct. 10% conditions, 200 respondents to less than 10% of all the female students at a large college. Large college, say 10,000 people or whatever. Success failure condition. The department expected NP equals 200 times 0.22 equals 44. Now, notice, let's just say NP is greater than 10 and NQ is greater than 10. You must show the math. Show your work. Okay, and then you must write your concluding sentence. This transition sentence, once you finish your preconditions, you must state, it's okay to use a normal model to describe the sampling distribution of the proportion of respondents with BMIs above 25. What do we got here? 5 W's. Okay? Context. Going back to day 1 of the course. Okay? If you don't use it, it will cost you. Okay, now you're going to state your statistic. This is from your sample. P hat equals 0.155. Okay, and you know the sample size, it's 200. So the standard deviation for the sampling distribution of P hat is going to be 0.22 times, it's going to be PQ over N. So 0.029. And now you have an approximately normal distribution. You have a mean and a standard deviation, and so you're going to go right into calculating the z-score, which you've done a million times. In this case, it won't be y minus mu, it'll be p hat minus p, which is the same thing, divided by the standard deviation of p hat. And you get a z-score of negative 2.24, which is very large, a large z-score, which means the probability of this occurring randomly is low. So I know that it will show up. I know that more than 2 standard deviations below the mean. So now you're writing the conclusion. The conclusion includes statistics. It includes the data, and it includes the context. And it includes a specific answer to the question. The question is this unusually small? Yes, it's unusually small. Why? Because it's negative 2.24 below P, below the stated population parameter of the proportion of 22-year-old U.S. students, of U.S. women with a BMI of 25 or more. Okay, now there's another conclusion, that's speculation, okay, and that's optional. All right, moving on. Just checking. 1, 2, 3. You want to poll. This you have to turn in. You'll have to turn this in tomorrow. So JC number 1. Poll a random sample of 100 students at a large university, 10,000 people. See if they're in favor of the proposed location of the new student center. Of course, you just get one number, your sample proportion P hat. But if you imagine all the possible samples of 100 students, now we're talking, the possible samples of one size 100 are probably in the millions. You could draw the imagined histogram of all the sample proportions. So let's say you made 10,000 samples of n equals 100. So that's 10,000 p hats, and n equals 100. What would it look like? It would look normal. Okay? And what would be in the middle? P. Okay, whatever that's the true proportion of students in favor of the new student center. Okay, that would be in the center, and this distribution would follow. It would be approximately normal. Okay, so it would follow the 68, 95, 99.7 rule. So that's number one. Two. Two. Where would the center be? Well, we answered that. It would be at the center. It would be the true proportion of the students in favor of the new student center. Why is that, by the way? Why would it center around the true proportion? And the reason is the samples are representative. They're random independent, not too big, not too small. If all the samples are representative, then they are going to cluster around the true center. And that'll be at the center of the true, whatever truth is, will be at the center of your distribution. Okay, if half the students are in favor of the plan, okay, P equals 0.5. What's the standard deviation? Okay, N equals 100. So, standard deviation of P hat equals, now you should show all this. Answering the question is not simply putting down a number. You've got to show your work. Okay, it's going to be PQ over N, which equals the square root of 0.5 times 0.5 over 100, which is, need some more writing space here, which is going to be 0.5 over 10, which is 0.05. So the standard deviation of P hat equals 0.05. Okay. Now, step-by-step example, extremely important. Now, let me just explain something to you here. The part on the left tells you what you have to do. The right-hand column shows you the work you must produce. Okay, to repeat, the left-hand column tells you what you have to do. The right-hand column tells you the work you have to produce. Okay, so 13% of the population is left-handed. That's a population parameter. Okay. We got 200 seats with 15 lefty seats. Okay. Now, in a class of 90 students, okay, so there's out of those 200 seats, there's 15 that are for left-handed students. So we got 90 kids. What's the probability there will not be enough seats for the left-handed students? Okay. So I want to find out the probability that in a group of 90 students, more than 15 will be left-handed. Now, 15 out of 90 is 1/6, which is 16.7% approximately. So I need the probability of finding more than 1/6 of the left-handed students out of a sample of 90. More than 16% are left-handed if the true population parameter is 13%. Okay. Independence is reasonable. Now, you're not told that it's independent. So you have to show some thinking here. Independence assumption. It is reasonable to assume that the probability that one student is left-handed is not changed by the fact that another student is right or left-handed. Okay, so this is not a course specifically geared towards left-handed or right-handed people, whatever that might be. Randomization. The 90 students in the class can be thought of as a random sample of students. Okay, so you just can't write random independent, check them off. You got to state why you think it's independent and why you think it's random. And if you don't do that, you don't get credit for it. And right away, if you don't do the preconditions, you are automatically down 50% of the credit for the answer. 10% condition, okay? Now, again, here you're making some assumptions, but you've got to state the assumption that you're making. Okay? Now, over to the next page. And you're still continuing with the preconditions, success and failure, and you're showing the math. Okay, now we're going to get into stating the parameters, sampling distribution model. P is 0.13. Conditions are satisfied. Model the sampling distribution of P hat with a model of 0.13. Remember, the standard deviation P hat, square root of PQ over N. So we got 0.035. Now you have a mean and a standard deviation, and you are going to evaluate the probability of P hat based on that distribution using the normal model, and you're going to use normal, so you get a z-score, P hat minus P, 0.167 minus 0.13, 0.035 equals 1.06. Not a very big z-score. Okay, so the probability. And how did we get that probability? Normal CDF. Okay, let me clear this. So, second virus, good old normal CDF, number 2. And I'm going to put in 1.06, comma 99, close parenthesis. And there's my 14.46%. Okay? So a lot of the execution of this it's very similar to what you've been doing already. In terms of the mechanics, there's really not much new going on here. Okay, and then you write your conclusion, contextualized, and including your final probability there. Okay, now that is probably enough. Let's look at this next page here. Okay. Now they go into the sampling distribution of a mean. Now, what they're showing you here is, I want to cover this next couple of pages just because it ties into the thing I was starting to talk about previously, and then when I was in the wrong place. Okay. So now we're talking about means. Now, means have sampling distributions just like proportions, but what you can see here is that as the sample size gets bigger, here, let's talk about that's down here. Okay. So what does the distribution look like if you throw one dice and you write down whatever number you get? Well, it's going to be uniform. Okay, no matter how many times you roll it, because your sample size is only 1. Now, if you do 2 dice, you're going to get a symmetric. You're going to get kind of a bell-shaped distribution. Actually, it's triangular shaped. It's not bell-shaped. It's not curving, and that's because the numbers can only go from, if you're throwing 2 dice, you can only go from 2 to 12. Or I'm sorry. You're averaging them. My apology. Okay, but still, it's not going to. The granularity is not enough to make it look like a normal curve. Okay, 3 dice. We're no longer looking triangular. Okay. Now it's starting to look kind of bell-shaped. Okay, and with 5 dice, we're starting to look normal. Okay. Now, as the sample size increases, the shape of the graph looks more and more normal. And then when we get up to 20 dice, now we definitely have a shape that follows the normal distribution. Okay, and it has the normal, it follows the 68, 95, 99.7 rule. But smaller than that, and then we start not having a normal distribution. Okay, so we have what's called the central limit theorem. This is a fundamental theorem of statistics, as it says right here. The sampling distribution of any mean becomes more normal as the sample size grows. Sampling distribution, okay? Now remember, what were we looking at here? These were averages. Okay. averages from one die. Okay. Now, well, average of two dies. Okay. Now it starts to look at least triangular and has more of a, well, both distributions are symmetric. Both of these are symmetric in that the right and left sides look similar. Three die, now we start getting, still not normal, but it's starting to have a curve. Four die, same thing, starting to have a curve, the average of the numbers. But it's not until we get up to 20 that we have a normal distribution. Okay. Now, we're not getting into the mathematics here, but what about, I want you to look at this paragraph here, okay? What about a really bimodal population, one that consists only of zeros and ones? The central limit theorem says that even means of samples from this population will follow a normal sampling distribution, as long as the sample size is big enough. But wait, suppose we have a categorical variable and we assign a 1 to each individual in the category and a 0 to each individual not in the category. And then we find the mean of these zeros and ones, which is the same as the sample proportion. Okay, the idea is, let's go further back in the paragraph here. The central limit theorem works. The central limit theorem says the sample size is big enough if n big enough, then either the p-hat or the name of the sample statistic is called y-bar for means will have approximately normal distribution if n is big enough. Then p-hat, then the sample statistics. So if n is big enough, then just say you're distributing a whole bunch of y-bars. Okay? And you got 10,000 y-bars. You got a y-bar, 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 10,000 y-bars. Now what are these going to distribute about? They're going to distribute about the true population mu, which is designated by the Greek letter m. Okay? Now, this is true even if the population does not have a normal distribution. Now, certainly the population for a categorical variable is what? A histogram of a categorical variable is going to look like a bar graph. Okay? In other words, this would be yes, and this would be no, or whatever. Okay? It's not normal. And yet, the statistics taken from this population, let's say this is the population. And yet, if we take samples from this population, thousands of them, and we take the p-hats, okay, we take a whole bunch of p-hats, let's say we take 10,000 p-hats from this population that's definitely not normally distributed, then we're going to end up, I don't know what's going on here, we're going to end up with a normal distribution of the p-hats centered around p. And the same thing goes for quantitative data. Here's the population. Suppose the population is heavily skewed, okay? Looks like this, all right? Or is bimodal, or you name it, okay? Nevertheless, the sampling distribution, so in other words, representative samples taken from that population will have a sampling distribution, that is, the statistics taken from those samples will distribute normally. Now, suppose I take a sample, a 1,000 person sample from a population on an opinion. Now, what's the distribution of the sample? What is the internal distribution of the sample? It's going to be bimodal or whatever. In other words, it's going to be just yeses and nos. Okay? So, the sampling distribution is the distribution of the sample statistics. The distribution of the sample is the internal shape of the sample. So if I take a large sample from a skewed population, the shape of the sample will be skewed, but the distribution of the sample statistics will be approximately normal. Okay, so here's the central limit theorem. So you need to look this paragraph over and take in what it's saying. Basically, what is it saying? That the distribution of the sample is not the same as the distribution of the sample statistic. Every sample is going to have a shape. The larger the sample, the more it will resemble the shape of the population. But the distribution of the statistic taken by those samples is always going to be normal, as long as the samples are representative and they're big enough. And that is it. Now you're ready to do some homework.